Okay, this is question 2 from module 4, June 2005. It's the pressure law, gas law question. So, in an experiment, the pressure of a fixed mass of gas at an ideal gas is increased slowly. The volume V of the gas and the corresponding pressure are measured. The temperature of the gas is held constant. The results of the experiment are plotted on two graphs. Okay, so on figure 2, sketch graphs to show the relationship between the quantities labelled on the axis. So we have V against P, and that is going to be a fairly simple inverse relationship looking something like so, right? And then we have PV against P. Well, what Boyle's law tells us is that PV is equal to a constant, so even if the pressure changes, this is a constant, therefore that's going to be a straight horizontal line going across. Label the quantity each of these, so that's T1 and that's T1 there. Then the experiment is repeated with the temperature increased. Sketch another two graphs to show how the relationships would change. Well, if the relationships change, well, first of all, this graph then simply moves further above, and that's T2, and the same here, that same graph going across T2 going across, so that should be a horizontal line. So we've two horizontal lines there. Use a ruler and draw those in. We then come to calculation. So we've got the pressure in the tube of a tire is 500 above atmospheric, so now that's interesting, that's 500 above atmospheric, so therefore straight away we're saying that that the pressure is equal to 100 kilopascals plus 500 kilopascals, which is 600 kilopascals. Okay, so that's the pressure in the tire. Is that the initial volume of the atmospheric pressure trapped in the barrel is 2 times 10 to the 4. The temperature of the air is 17. So again, that's 17. So 17 degrees Celsius is going to be equal to, I need to add on 273, so that's 290 Kelvin. So those are the first two things that we've noted as we've gone through. And then when the piston compresses, the air volume is reduced to 4 times. So we've got V1, we've got V2, and we've got T1, and we're looking for the new temperature. So what we're going to say is then P1 V1 over T1 equals P2 V2 over T2. And when we're using this, as long as the units are consistent and temperatures in Kelvin, then everything else will take care of itself. So the pressure, initial volume of it is atmospheric pressure, therefore we have 100 times, and the volume was 2 times 10 to the minus 4 over 290 is equal to 600 times 4 times 10 to the minus 5 divided by T2. Oops, so that's 100 times 2 times 10 to the minus 4, so this is the atmospheric pressure before we started squeezing it, and then that comes up to 600 whenever it's finished. So that means that T2 is going to be equal to, so that's 290, T2 comes up here, so we get 290 times 600 times 4 times 10 to the minus 5 divided by then 100 kilopascals times 2 times 10 to the minus 4. So that's going to go into that 6, multiply that out, and T2 is equal to 348 Kelvin. So minus 273 is equal to 75 degrees Celsius. So 75 degrees Celsius is the answer to that question. Making use of kinetic theory, ideas explained carefully. So the kinetic theory is to do with the movement of the molecules. So we're trying to explain why the pressure and the temperature of the air in the pump increase. So increase for one push stroke of the piston and the pump. So what we're looking at now is that as the piston moves down, so as the piston moves down, the volume of gas decreases. In this case, the volume of air decreases. So the molecules have less room and so make more collisions. Per second. So they're making more collisions per second. Therefore, the pressure increases. Okay. As the piston moves down, the piston does work on the molecules and increases their kinetic energy. So the average temperature rises. Okay, so kinetic energy goes up, more collisions per second, pressure goes up, kinetic energy goes up, average temperature goes up.